Hello, my name is Karen Glauda, and I will be presenting my action research, The Impact of Interactive Science Simulations, a Student Engagement and Conceptual Understanding in an 8th grade Earth Science Classroom. This study focuses on how interactive science simulations can support student learning, engagement, and understanding within a middle school or science classroom that is aligned to the New York State science learning standards. Earth and space science includes many abstract concepts that students cannot directly observe in a classroom setting. So processes such as plate tectonics, Earth system interactions, and energy transfer often occur at large spatial and temporal scales. Traditional instruction relies heavily on lectures, textbooks, and static diagrams that can make it difficult for students to visualize and understand these concepts. Through my own classroom observations, I noticed that students were more engaged and demonstrated stronger explanations when simulations were incorporated into lessons. This led me to investigate how interactive simulations influence both student engagement and conceptual understandings. It's also going to help any school that is changing to the current NISLIS standards, where they rely on the 5 science practices that rely heavily on students' hands-on learning versus chalk and talk. The primary research question guiding the study was, how do interactive science simulations affect student engagement? And then there were 3 sub-questions. How do simulations support understanding of abstract earth science concepts? And how do students describe their learning experiences when simulations are used? And how will this overall help them prepare for the regions? So the population and setting was at Herrick's Middle School in Albertson, New York, in the 8th grade accelerated earth science classroom. There were approximately 30 students between the ages of 12 and 14, and the classroom environment was supportive and constructive based on inquiry-based learning approaches set forth by the NISLIS standards. So the literature consistently supports the use of simulations in science education when they are paired with teacher guidance and inquiry-based learning. Research by simulations improve conceptual understanding by helping students visualize abstract scientific processes and explore cause and effect relationships. However, the literature also emphasized that simulations are most effective when they include scaffolding, guided questioning, and opportunities for reflection. Simulations alone are not enough. Effective instruction and teacher facilitation remain critical components of student learning, which the NISLIS standards do put forth that there does have to be a certain level of scaffolding as well as teacher instruction. This action research study took place over a 4-week instructional period during regular classroom instruction. Interactive simulations were aligned into the existing Earth and space science curriculum through whole class instruction, small group activities, and independent exploration. Lessons followed an inquiry-based format that included engagement, exploration, explanation, elaboration, and evaluation. Students manipulated variables within simulations, observed outcomes, and used evidence from the simulations to support scientific explanations. Throughout the study, instructional decisions were adjusted based on formative feedback and student understanding. So again, this was the basic project procedure. We started with baseline assessments and initial simulation introduction. We focused primarily in the topics of plate tectonics and astronomy because those were the 2 largest temporal and spatial topics that we had. And during weeks 2 and 3, we used a guided use of science simulations with lab activities and quizzes. And then week 4, we had a summit assessment and student reflection collection. Multiple forms of data were collected to provide a complete picture of student learning and engagement. So quantitative data included quiz scores, formative assessments, exit tickets, and summative assessments aligned to the NISLIS standards. And then qualitative data included student reflections, written explanations, and teacher observation notes collected through structured observation checklists. And then using multiple sources of data allowed for triangulation and helped strengthen the credibility of the findings. It was also very telling to see what my students liked and what they didn't like as we move forward with these new standards and get ready for the Regents exam. Some challenges and unexpected events that occurred during the action research implementation process was pacing changes. Again, we had to change based on how the students were learning the overall concepts. So it couldn't, if the students were not learning at the rate that we needed to, we couldn't introduce the simulations at a time. Attendance variability, so whether students were there every single day or not, or if there were pullouts for music or field trips. Instructional support, so any student with differentiation needed, and of course technical issues. So if the simulation didn't work, or if we were having issues with how students used it. And the study also involved a small sample size, so the convenient sampling within one classroom setting limits generability. Again, the sample size limits generability. Additionally, because I served as both the teacher and the researcher, there is potential for bias. To address this, I used consistent procedures, multiple data resources, and triangulation throughout the study. The short duration of the study is also a limitation, as longer term impacts on retention and transfer of knowledge were not examined. And then, of course, the reflection accuracy. Some key findings that I had were that through the assessments, reflections, exit tickets, and lab activities, I found that they influenced my understanding of both teaching and learning. It reinforced the importance of student-centered instruction and shows how interactive simulations can create opportunities for deeper inquiry, discussions, and conceptual understanding. My perspective shifted from viewing technology simply as an engagement tool to recognizing it as meaningful support for scientific reasoning, evidence-based learning when paired with intentional instruction. I also found that it increased student engagement because they were able to have more of a hands-on lab experience than just learning from notes. It gave students stronger evidence-based explanations because they were able to be more reflective about the process and understand why things were happening. And it very much enhanced their inquiry skills as we moved to the state labs where they really needed to have those. So again, this action research developed my understanding of how flexible student-centered environments foster meaningful learning. Through iterative cycles, I gained enhanced awareness of pacing, instructional supports, and engagement strategies that truly resonate with students. This experience reinforced the importance of adapting simulations to meet diverse student needs and learning styles. So thank you for your attention and thank you for listening.